In this video, we will talk about graphs of an equation in x and y and some of their basic properties. So the graph of an equation in x and y is going to consist simply of all of the points or ordered pair x comma y that satisfy the given equation. Now, one thing that can help us with determining the shape of a graph is to think about symmetries that are present. If we have an arbitrary graph, we say that it is symmetric with respect to the y-axis if whenever the point xy is on the graph, so is minus xy. So that is to say that the graph is a mirror image of itself or a reflection about that y-axis. The simple way to check this is that when you replace an x by minus x in your entire equation, it remains the same. Think if you have y equals x squared and you replace it by a minus x, it's still the same equation because that minus gets squared. Similarly, we would say that the graph is symmetric to the x-axis if whenever a point xy is on the graph, so is x minus y, i.e. your graph is a reflection of itself across that x-axis. A simple way of checking this is by seeing that if you replace every y in your equation with a minus y, it remains the same. A last type of symmetry is symmetry with respect to the origin. A graph is symmetric with respect to the origin if whenever a point xy is on the graph, so is its opposite, minus x minus y. And a simple way of checking this is if you replace each x by a minus x and y by a minus y, you're going to end up with the same equation. For example, with y equals x cubed, if it became a minus y and a minus x, a minus sign would factor out of both sides and cancel off. So let's look at a few basic examples. Oh, before getting into those examples, let's consider kind of the basic forms that we might encounter to see. So graphs that we should be very familiar with would be, say, quadratic graphs. If you have x squared, it opens upward with its vertex at the origin. Minus x squared opens downward with its vertex at the origin. And as you add on to this, plus bx plus c plus bx plus c, if the leading coefficient, that a, is positive, your quadratic opens upward. If it's negative, your quadratic opens downward. Very similar here in terms of cubics. You have y equals x cubed, the basic cubic, and y equals minus x cubed. And if you add on additional terms, the shape is going to be determined by whatever the sign of that leading coefficient is. If it's a positive a value, it looks like the shape of x cubed, somehow shift it. Similarly, if that a value is negative, it looks or takes on that basic form of minus x cubed. X equals y squared would be a quadratic opening in that positive x direction. Y equals square root x, common function, and also x equals y cubed is given here as well. So for the equation x squared plus y squared minus 2y equals 8, let's check it for symmetries and find all of the x and the y intercepts. Then we'll sketch the graph. Okay, so in terms of symmetry, so let's first think about the y-axis. So for y-axis symmetry, what that would mean is if we plug in a minus x everywhere we see an x, the equation would not change. So if we plug in a minus x, we would have x squared plus y squared minus 2y equals 8. So check. This equation is symmetric about the y-axis. So symmetric about the y-axis. In terms of x-axis symmetry, we need to think about plugging in minus y. So x squared plus minus y squared minus 2 times minus y equals 8. and that would be x squared plus y squared plus 2y equals 8. So this last term here is changing, so I'll just simply write a no, not symmetric about the x-axis. The last type of symmetry is symmetry with respect to the origin. So to check this, we want to plug in minus x and minus y. And we're going to have the same problem that we had a moment ago. Because when you do so, the first two terms rewrite nicely, but that third term is plus 2y equals 8. So once again, that same term is troublesome. So no, it is not symmetric about the origin. So let's go ahead and think about maybe what the shape of this graph would look like. Seeing the x squared plus y squared minus 2y equals 8, and thinking about some of the previous material we've encountered, this looks an awful lot like something that might be the equation of a circle. And how we would know is we put it in that standard form by completing the square in the y. To complete the square in the y squared minus 2y, divide minus 2 by 2, looks like it's the first two terms of y minus 1 quantity squared. Now y minus 1 quantity squared is y squared minus 2y plus 1. So in order for this to work, I need to put a plus 1 on the left and a plus 1 on the right. So our graph is going to be the equation of a circle. Its center is going to be the point 0, 1, and its radius is 3. And we can see this in the picture, a circle with center 0, 1, and the radius is 3. Now something else we've been asked to do is to find all of the x and y intercepts. So if I want to find the x-intercept, what we do is we set y equal to 0, and we solve for those corresponding x values. So x squared plus 0 squared minus 2 times 0 equals 8. X squared equals 8. So x is plus or minus the square root of 8. So for our x-intercepts, we have square root of 8 comma 0 and minus the square root of 8 comma 0. And we can see those in our picture. We'll have minus square root 8, 0, square root 8, 0. To find the y-intercept, we take a similar approach, except here we plug in x equals 0 and solve for the corresponding y value. So 0 squared plus y squared minus 2y equals 8. This equation becomes y squared minus 2y minus 8 equals 0. And this factors nicely. You think two numbers that multiply to minus 8 but add to minus 2. So this is y minus 4 times y plus 2 equals 0. So y equals 4 and y equals minus 2. So the y-intercepts will be the points 0 comma minus 2 and 0 comma 4. And we can see these in our picture. 0 minus 2 and 0, 4. So let's do the same thing with a second example. Let's check the graph x equals y squared minus 3 for symmetries, and then find the x and y intercepts, sketch the graph. So let's once again start with symmetries. So let's check first for y-axis symmetry. For y-axis symmetry, we want to know if we plug in minus x, we will get out the same thing, the same equation. So minus x equals y squared minus 3. So No, because of that minus with the x, it is not symmetric to the y-axis. So we check the x-axis symmetry. So replace each y by minus y. So minus y squared minus 3. This is equivalent to x equals y squared minus 3. So check. The same equation we started with. So our graph is symmetric to the x-axis. Lastly, we can think about an origin symmetry. To be symmetric about the origin, you replace each x with a minus x and each y with a minus y. When you do so, you end up with minus x equals y squared minus 3. And the left-hand side is troublesome, just like it was with the y-axis symmetry. So no, not symmetric about the origin. Now in terms of graphing this, well, looking at the equation itself, we know that this is a quadratic, so it's going to have a graph which has the shape of a parabola. And because it's x equals y squared, it's going to be opening up in that positive x direction, so opening up to the right. So really to sketch this, once we find the x-intercepts and the y-intercepts, we should be good to go. So to find the x-intercepts, we set y equal to 0 and solve for the corresponding x values. So x equals 0 squared minus 3 equals 3. So the x-intercept, minus 3, is minus 3 comma 0. Similarly, to find the y-intercept, we set x equal to 0 and we solve for y. 0 equals y squared minus 3. 3 equals y squared. So plus or minus the square root of 3 is equal to y. So our y-intercepts would be the numbers 0 minus the square root of 3 and 0 positive the square root of 3. So let's put all this information together. Our graph is a quadratic equation as the shape of a parabola. We said it opens to the right in that positive x direction. Its x-intercept we found to be minus 3, 0. And we found the y-intercepts to be the points 0 minus the square root of 3 and 0 positive the square root of 3.